I do want to grab your attention on the next slide. This is about hold time constraint, which is somewhat counterintuitive, right, to many people initially. Right? So for hold time delay, once again, think about the definition. It's about the constraint, right? That's after the clock catch. You hold the input steady after the clock catch for this so-called T hold amount of time. Okay. And this is where we have to consider the minimum propagation delay. Why is that the case? Right? See here, I'm showing the equation directly. So this is how we determine whether we have a hold time violation or not. This is independent of the clock period. Basically, T clock is not in this inequality. Right? So we only need to consider the flip-flop, the minimum delay of flip-flop, and the minimum delay of the completion logic. So to help you understand this, maybe I can ask you guys a question. So what is the worst case scenario for us to have a hold time violation? Because what is the worst case scenario that we have to handle when we want to meet the hold time? Think about this completion logic, right? So we cannot change the spec for flip-flop, right? We cannot change the spec, right, for T setup or T hold. But let's say we can vary the completion logic. So we have a different kind of logic in our design, right? I'm asking you, what is the worst case scenario? To rephrase my question, right? So again, we have these signals, right? Although I'm calling the bundle of the signals, right, as D2, right, the inputs to the flip-flop 2. So really the question is, when does D2 change? And what is the scenario when D2 change quicker, right, after the clock catch? So that's the worst case scenario. What is that? Do we want to add more completion logic, or we want to have less completion logic for us to have a more challenging case for setup, for meeting hold time? Less, right? What is the extreme case? The extreme case is very good, right? Extreme case is this. Basically nothing in between. And again, let's assume that we have very short wire. I'm going to talk about wire delay very soon. Okay, we have been assuming that we have 0 wire delays, right? But in this case, right, we have a very short wire, so 0 wire delay again. So this is the worst case scenario, right? Let's try to mix, try to understand this, try to reason about this a little bit more. Okay, first, let's focus on FF2 again, right? FF2. So this is where we want D2 to be steady, very stable after clock catch. Right? So if you look at this clock catch, right? So we have a clock catch here, right, the green line and this dash line. So the gap between the green line and the dash line, this is the hold time window, right? This is the hold time window. And of course, right, in the second edge, the next clock edge, we also have this hold time window. We need to meet this, right, every clock cycle. Right? But we only need to focus on one of this. Let's just focus on this gap, right? This is a T hold. Okay. So add this clock edge over here, right? Clock edge in, right? Input. Right? We first need to look at Q1 because Q1 is directly connected to D2. The moment that Q1 changes, D2 changes, right? This is the worst case scenario. The moment there's a transition for Q1, then D2 will be transitioning as well. Right? So here in is 1, right before the clock edge. And after clock edge, Q1 start to make this transition from 0 to 1. What I'm asking you guys is, what is this gap? So what is this? What is this gap? Between the green edge and the time that Q1 is making the transition. What is that term? What is that parameter? What does this gap mean? TFFPD, very good. Right. Look at middle point. So this gap is TFFPD. Okay. Do you want to consider mean or max for TFF mean? In this case, mean, right? The minimum delay is the worst case scenario. We're going to consider the case where it basically the change happens in the soonest possible scenario. Right? You want to consider mean here. Okay. So then, what is the relationship between this for us to meet the whole time? We already have T hold. You have TFFPD min. What is the relationship between these two for us to have a stable condition? Less than, equal, greater than equal. Very good. Yes, right. Any questions? If you understand this part, you will almost get whole time, right? This is a whole time requirement. How we handle this whole time requirement. This is a worst case scenario. Okay. All right. So if this is clear, then we have zero, right? Zero conditional logic, right? And zero wire delay. So if you do have some cloud here, conditional cloud, and let's say the delay is T com, right? So how do you plug this in? How do you consider this? How do you update the right hand side, the left hand side? Do we do plus? Do we do TFFPD plus or minus? Plus, right? Of course, plus. Okay, and we also want to pick out the mean. This is the worst case. So we want to plus this, right? T com mean, if there's anything, if there's any condition delay. That's how we meet the whole time. Just to make sure that this gap, right? Is this gap, in this case, the gap, right, between the clock edge and the transition D2, right? For this case, the transition D2, right? So this happens together with the transition of a Q1, right? In this worst case scenario, with a 0 wire delay, with no conditional logic. We want to make sure this gap is wider than the gap defined, than the window defined by whole time. This is what we're doing. All right, so if this is clear, so let's come back here, and this is basically what we got, right? This is what we got. Right? If this is still not clear to you guys, let's look quiz again. Right. You guys can again use the reference time. You can define T0 and define, this is the basic 0 plus T hold, right? And you can just use the trick that I showed you to reason about this. All right. Any questions about T hold? Whole time violation? Okay. All right. So this is the TFFD, right? The gap. And this is the equation. All right. So one more exercise. Same template, pair of flip-flops. I think this is the same parameter, maybe not, slightly different. Okay, they don't matter because. So what is the whole time? What is it met or not met, the whole time? Do we have a violation or not? Okay, so what numbers do we pick up? This one, right? And this one. We want to make sure that 1 plus 3, right, is greater or equal than 1, which is true in this case. Okay, we do have a whole time, right? So we do meet the whole time constraint. All right, so there's some question. What was the time until we could read Q? what was the time until we could read Q? We're talking about this one? This one, Q1 or Q? Is that right?
Oh, I mean on the previous slide. Like until we could read Q2.
Until we can read Q2. Oh, Q2. Q2 is sort of symmetric to Q, right? So basically after clock edge, we add up a TFFPD, right? Over here. So for any flip-flop, it's the same. Right? We have the same flip-flop. Any one of them, the Q, we have this clock to Q delay or FFPD, TFFPD, right? They are supposed to be stable after this period. That's it. Okay. And also for you guys who are still working on quiz, you don't need to add TFFPD twice, right? Because the other one happens after the next clock edge. Per clock period, you only need to use it once. Okay. Hopefully so far so good. Right. Again, some of this may not be that intuitive, right? We may have to wrap our brain around a bit. But if you have questions, make sure you ask. So here's another interesting concept. Right? Yeah, if it is not confusing enough, right? I have to unfortunately add to the confusion. We also have to deal with something called clock skews. Right? So make sure that you also pay attention to these few slides. It is very important. We are going to be seeing this. We're going to be working on problems like this over and over again. We also, you guys will pretty much, I'm pretty much sure that you guys will see questions about time analysis and clock skews in the second problem. Okay, actually, many, what I heard is many, when you guys interview for chip companies, many people also ask you questions when they do the interview about clock skews and such. All right, so this is where we actually consider the wire delay. Okay, so far we have been assuming that there's really no wire delay. Right? We have a global signal and the clock can reach right, different endpoints. So by endpoints, I'm talking about this, right? These are endpoints of the clock signal. They can reach different endpoints at the same time. Okay, but again, this is not, this is just the ideal case, right? It's actually not practical in the realistic case. So we do have wire delay, even for the clock signal. So that's where we may have the skews. So basically, different flip-flops may see the clock hash at different times. Okay. So what do we do about this? Right. First, we need to make sure that the waveform reflects this delay. In this case, so I'm assuming that the clock signal is traveling right from the right-hand side, and then there's this non-trivial delay right on the wire. So in this case, FF2 will see the clock. There's a clock tick sooner than FF1. Clear? So basically, the waveform looks like this. Clock 1 is somewhat delayed, right? There's this gap here. You look at this rising edge of clock 2 and the rising edge of clock 1. There's this gap here, and we call this T skew. Okay, is it good or bad in this case for meeting the setup time constraint? Or maybe I can ask you guys another question. I can rephrase the question. Coming back to the exam analogy. Okay, just want to give you guys some intuition. We do have clock skews, right? We do need to deal with clock skews actually in our problem 1. Think about this, right? We were going through this transition to daylight saving time, right? The exam is supposed to happen at 1 p.m., right? But let's say you forgot about this transition, right, from EST to EDT. So on your watch is still 12. Is it good or bad for you? Good. Think again. Why is it good? Okay, so at 1 p.m. the exam has already started, right? But on your watch, you still have 12, right? So which means when you enter the exam, you only have 15 minutes left. to work on the problems. That's a clock skew, right? This is the clock skew in the in this exam analogy. Make sense? Okay. All right. So this is that, right? What does this mean? So intuitively, this means that effectively, because of the clock skew, right, the sort of the clock period gets narrowed somehow, right? This is the analogy. This is the intuition. But let's try to analyze this. Okay. First, we also have min and max. Right? We usually have this different depending on the condition of the circuit. You may have a maximum worst case, or minimum case, or a maximum case, right? So let's look at how we actually solve this set of time constraint. Then the clock skew is in the picture. Once again, just want to be clear. Our assumption is that in this case, right, clock 1, right, this clock 1 is delayed. Right? So basically, we have a long wire. So going from here to here. Okay, FF1 sees the clock later. So what do we do about this? How do we analyze the cycle time requirement? Once again, let's use the reference time. Let's use this edge. Assuming this one is my reference clock 1. So let's say T0, this is my reference time, right? It's 0 here. Okay. So what is this? What is this clock edge? What is this point? Let me know. Okay. This is minus T skew, right? Right? And when's the deadline for FF2? FF2, D2 needs to be stable, right? Where's the deadline for D2 to be stable? We need to look at this point, right? But first, let's look at the next clock edge of clock 2. Next edge of clock 2. This point is what? T clock what? Based on the, right, with respect to the reference time. With respect to this reference time. What is this? It's T clock minus T skew, right? Right? Basically, this one plus 1 cycle. Is it clear? Again, this is T1, right? I'm defining this point as T1. Let's say I'm defining this point as T2. Hopefully this is clear. Any questions? If you have a question, just ask. Where is clock defined from? T clock. Where is T clock defined from? Good question. So this is a variable right now. Okay, this is just a symbol for us right now. This is a bit our cycle time. Right? And we assume that we still have a global signal, right? We have global clock. We have the same clock period, right? Which is T clock. And this one, right? So this period is basically T clock, right? And this is something that we need to solve for, but we can just use this one, right? We can just say use a T clock. But is this clear? Makes sense, right? And of course, the deadline now is this point, right? We have the theta time constraint. Deadline is T2 minus T setup. T2 is here, which is T clock minus T skew minus T setup. Right? Okay. Steve's asking, this wouldn't change the value of T setup, T hold? No. Right. Again, these are constant, right? Like I said, these are the constant parameters. Of course, the skew is also constant, right? Based on the chip, based on the actual chip layout, we can derive these values, the skews. Okay. All we need to do is we want to analyze the clock period. What exactly is T clock? So far, so good. Right. This is the new, right, new deadline. If this is clear, then the rest is very similar, right? We just need to add up So what is the arrival? What's the arrival time? When does this thing arrive? Again, with respect to T0, the reference time. What's the arrival time? Guys, don't be confused by the, right, there's two clocks, right? I already have defined, right, the reference time for clock one. Okay, very good, right? The arrival time is still TFF. I keep saying T, right, this one. Right. Because for the arrival, we look at clock one, right? We look at FF1. All right, so is this clear? Then, right, then we can look at waveform again, right? So we already analyzed this, right? We look at the TFFP, right, is arrival, right? We just add it up. We have already defined the deadline over here. Okay, so we just T, right, clock minus T skew minus T setup. So we just have to set up the inequality. So which is this, right? This is the same, right? You can also move it here, right? You can do a minus. You can move it here. This is the rearranged term. Okay. And here we look at the max skew. I'm going to talk about why we use max and mean, right? When we use mean and max, maybe next time. But at least on the first order, I hope this is making sense, right? This is how we incorporate a skew into the analysis, right? So we call this a negative clock skew. So this is where flip-flop one, or we call it standing flip-flop, receive the clock after the receiving flip-flop, okay, later than the receiving flip, which is later than FF2. Of course, you can ask, right, what about the other scenario? So when FF2 received the clock later than FF1, coming back to the exam analogy, is it good or bad for you guys? If this scenario is reversed, that's good, right? Effectively, you have more time. Right? Same for meeting the setup time. So in this case, it's bad, right? That's why we call it harmful skew for setup time. This is harmful if we have a negative clock skew, if F1 sees the clock later than FF2. And in the other scenario, if FF2 sees the clock later, so this opposite scenario, we have something called positive clock skew. Okay, and this is where the equation, you guys can go through the same exercise, right? Same exercise, we define the reference time here, right? There's a T0, 0, we use right, clock one as a reference clock. Then this edge is T skew, right? And then, right, so then this one, right? This one is T clock plus T skew, right? See here, there's a plus. So that's why, right, there's a plus here. That's why it's called positive. It's a positive skew. Okay. And the deadlines here, right? Deadlines here, which is T clock plus T skew minus T setup. Okay. And the arrival time is still the same. Right, this is arrival. Any questions? Lauren's asking what happens if we have 3 clocks? Good question. So we can analyze this. I can see whether we have other problems in the homework or maybe some practice questions for you guys to practice about the 3 clocks. But the key principle is the same. We look at every single pair. We look at every single pair of flip-flops. Okay, so there we just need to look at the reference, the clocks for 2 flip-flops per pair. Okay, and then we look at all these combinations. We look at all the pairs, and we look at the worst case scenario. Can you have both negative and positive clock skew? Very good. Yes, when you have more than 2 flip-flops, you may have both negative and positive. But per pair, we can only have either negative or positive. Make sense? All right. Okay, so this is harmful. The previous one's harmful, this one's beneficial, right? Because effectively, this thing is, right, so widening the clock, right? Widening the time for the signal to propagate. Also, real quick, see here, we are using mean. I'm going to talk about this a little bit more next time, but think about it, right? So why are we using max in the previous slide? And here we are using mean. So this is the homework for you guys. Okay. All right, so real quick, maybe just one more minute. So for you guys to do one more exercise before we go. Okay. Here's the setup. F1 arrives at, F1 sees the clock at least 4 nanoseconds earlier than FF2. Is this a harmful skew or beneficial skew? Beneficial. This is positive, right? FF2 sees the clock later than FF1. All right, so that's that. What is the best achievable cycle time? Very good, 8, right? Why is that? We pick out these numbers, right? We look at setup time, and of course the skew is here. So this is the minimal skew. The arrival time is 2 plus 7, right? Okay, and we have the setup as well, right? We need to do the setup. Setup is 3, and we do a minus 4. This is 8. Okay, if this is not clear, and this is the derivation, right? Okay, so this is the arrival time, right? If you move the setup to the right hand side, you have the deadline, right? And I'm going to talk about this a little bit more. Why do we use min, not max? And this is how we get 8 nanoseconds. All right. Any last minute question? Okay, if not, we are done. I'll see you guys on Thursday, and make sure to turn in your quiz. Okay, thank you guys.